honorable speakers, all the distinguished guests, ladies and gentlemen. I'm Jacob Huang, the Executive Director of Institute for Advanced Study, IAS, in City University of Hong Kong. And IAS in City University of Hong Kong was established in 2015. It's only less than 3 years ago. So it's a very young institute. But we try very hard to create a platform in CDU to link the world-class scholar with the CDU and also local Hong Kong scholar to explore this beauty of science and technology. Yeah, so many people ask me, what's your IAS specialty? And according to our President Gore, it must be pure science, academic science. So that means mathematics, physics, chemistry, material science, and bioscience. So far, we have 27 senior fellows. All of them are Nobel laureates and the very important academicians in the world. So today, welcome all of you to Materials Summit. And we have roughly separated into 3 groups, namely structural material, followed by the materials performance, and the functional materials. And each speaker will only have 8 minutes. So at about 6 minutes, we have a student helper to show you 2 minutes left. Oh, okay, yeah. And at the end of your lectures, 8 minutes, there is a ring. Yeah, want to try that? Okay, yeah. Not only one, just keep pushing, yeah. But anyway, after the 10th speaker, the lecture, we still have about 30 to 45 minutes for panel discussion. So today, only for the 10th speaker. So if the audience, you do have a question, you can send an email to me. So I will send to the corresponding speakers because the time limit, I'm sorry. So I think I don't waste any time. We start from the first group. Let's give a big hand to Professor GLEITER, Herbert GLEITER.
Thank you very much, Jacob. The talk I want to give is, or the topic is shown up here. What I want to do is to show you or convince you that nano-glasses, this is a topic I'm talking about, present a new kind of non-crystalline solids different from the glasses we have today. And secondly, they may open the way to a new generation of technologies. Before doing that, let me remind you that today's technology have a strong preference for crystalline materials, metals, semiconductors, ceramics. Almost all the devices we have in technology are made out of crystals. And the reason is very simple. By introducing crystal defects or chemical defects, we can manipulate the properties of crystals, and that is what we need for devices. 2 examples are shown here. Crystal defects, a high-resolution micrograph of palladium, and here is a boundary, and you can see that the atomic structure in the boundary is changed, and this change changes the properties dramatically. Similarly, when we introduce chemical defect, this is a 2-phase material, silver and iron. In the interface, we get new chemical environments. Again, that changes the properties. In glasses, the situation is quite different. What we do, we take the melt, cool it, and we inherit the melt structure at the glass transition temperature. An example is shown here. A 2-dimensional silicon dioxide glass where we have a random arrangement of atoms. You cannot introduce similar structural defects and similar chemical defects, and therefore we cannot manipulate the properties of glasses in the same way what we can do with crystals. Now the question is, could we do that? And then we would open the door, of course, to use crystals in a similar way as we can use glasses today. And I think, and this is what I want to show you, that we can do it. And the way to do it is by changing the way we prepare the materials, the glass materials. We take not a big chunk of glass, but we break it up in tiny droplets, a few nanometers in size, cool the droplets to glassy clusters, and then we take these glassy clusters and consolidate them into a solid, which consists of the clusters and the interfaces in between. And it's these interfaces, that's what I want to show is, that open the way to a new state of non-crystalline matter. with a new atomic structure, new electronic structure, and new properties different from the glasses you have today. And let me show you that by showing some of the experimental observation. This is a transmission micrograph of a gold glass. It looks like a polycrystal. You can see bright areas and dark lines in between. The bright areas are the glassy regions, and the dark lines are these interfaces, the interfaces which I showed you. The interfaces I showed you before. These interfaces are these dark lines in this picture. And these dark lines, we know from diffraction, from electron microscopy, spectroscopy, are the glassy interfaces. And here comes the big surprise that their density is about 15% lower than the density of a glass. Very dramatic. If you go crystal to a glass, you change the density by 1–2%. Different nearest neighbors and different short-range order. Here you see the radial distribution function of such a glass interface, and here the radial distribution function of a melt-spun glass with the same chemical composition. But not only changes the atomic structure, also the electronic structure changes. Here is the Mössbauer spectrum of the glassy region. It's a single line indicating it's a paramagnetic material, and here is the Mössbauer spectrum of the interfaces. It's a ferromagnetic material. And what we find in the end tells us that the structural model of such a nanoglass is we have two components, the glassy components, and then these new structures in between, which I called interfaces. And these interfaces have a new atomic structure, a new electronic structure, and they have all, and this is important, all the interfaces have the same structure. We just get one spectrum. And moreover, if we destroy these interfaces by rolling or irradiation, they always come back with exactly the same structure everywhere, and they remain unchanged when you anneal them, not like glasses where they relax, but they remain. All of that can be understood or suggest that these interfaces represent the lowest energy state of non-crystalline matter. If that is so, of course, then we expect new properties. And the answer, is that so? Yes. I'll show you here two examples. This is a ferromagnetism in a nanoglass. Here is a magnetization versus magnetic field. The melt-spun ribbon is a straight line, paramagnetic. The nanoglass is S-shaped curve, indicating it's a ferromagnet. Chemically, the same thing, new structure. And a mathematically very attractive thing is this, the biocompatibility of a nanoglass. Here is plotted the cell growth rate as a function of time. And the cells, these are osteoblast cells at the surface of the glass. They hardly grow. And when you put them on a nanoglass, they grow like mad, up to a factor 100 times faster, which means when you coat, for example, a tooth and you put it in, it does not grow in within days or weeks, it grows in within minutes. Now a new world opens up when so far I've talked about nanoglasses of one component. Now a new world opens up when we take nanoglasses of two components that are immiscible in the crystalline state. And I'll show you the two examples. One where the components have the same chemical bonds and different. Here with the same chemical bonds, it's a nanoglass made up of iron scandium and of copper scandium clusters. And when we put them together, the compositional map looks like this, very large fluctuations. But now comes the surprise. If you take these nanoglass mixtures only at 100 centigrade for a few hours, you see that they start mixing and they form an amorphous solid solution. And this is surprising because copper and iron is insoluble in crystalline state, and here you can dissolve it. Even more surprising effect was this: when we take an ionic glass, a nanoglassy cluster, and a metallic glassy cluster, and we bring them together, we of course get big fluctuations in the thing. This is silicon dioxide and a palladium nanoglass, but after annealing only 3 hours, 250, they start mixing, and what we get is a solid solution of an ionic material in a metal of palladium and silicon dioxide. It's a very uniform thing. Now, let me finish by speculating about the future. Well, in the past, what we have done so far is the technological applications of crystalline materials. They have led us or opened the door to a technology age where we are in, which is controlled by crystals, essentially. Now, nanoglasses are very similar to what we have in the crystalline material. It's new properties, new structures, new chemistry. And so by applying these nano-glasses, that may open the door to a new age of technologies, a glass age, because to any crystalline material we have today, we can produce a nanocrystalline, a nanoglassy material, but with new properties, new structure, new chemistry. And so the hope is that these nano-glasses may open the door to a new age of technologies. Now comes the catch. At the moment, it's very expensive to produce these nano-glass, but if we find a way to produce them in large quantities economically, then the door should be opened. We have new materials, new structures, new chemical composition. No reason why that shouldn't be used. Let me finish by showing you all the names that have contributed to this 8 minutes talk from Japan, from China, from India, from Europe, as well as from the United States. And these are the 2 institutes where most of the work has been carried out. Well, 8 minutes.
The second talk given by Professor Lih-Juann.
I really feel honored to give the shortest talk in my life. Thank you, Jacob. Actually, I tried to solve the most critical problem of structured material last 300 years. We hope they address these issues, okay? The title is High Entropy Alloy and the Design of Structured Material. The co-worker is Yang Tao. He's my graduate student here. What's the critical issue? I think most people know for critical issues for this structured materials, what is strength ductility trade-off? We know very well, okay? Second is deformation instability. The early necking with low uniform elongation. The higher strength, you have worse its problem, such as small grain size materials. Another one is the embrittlement at low temperature, lower temperature, it will become brittle. Okay, I want to point out important. High entropy alloys are the potential material for studying and resolve all these critical issues. I'll make some point here. In case you are not familiar with high entropy alloy, okay, I make a comparison for conventional alloys and high entropy alloy. Use a ternary system with pointer. Pointer is here. Okay, this ternary, right? Conventional material is based on cobalt base here, iron base, nickel base. The high entropies, we combine these together, work in this area, make a new area. Okay, what's the big deal? The big deal is here. If you make these 3 together, get new FCC phase. This FCC phase is different from conventional nickel-based material, which have different properties, which give a unique behavior of this new FCC phase. Okay, showing here. Okay, what is a FCC type high entropy alloy? Show no embrittlement at low temperature. Okay, as shown here, this is work by Professor RITCHIE, and many people did similar work for different kind of high entropy alloy. You can see here the room temperature, degree temperature, so cryogenic temperature. You see when temperature decrease, the material becomes harder and ductility becomes high. Okay, this is very unique, not for this material, for many high entropy alloys. So high entropy alloys have these characters because when you mix elements together, you lower the stacking forward energy. So in this case, during deformation, you generate more defect structure like microtune and stacking forward, which give you continually hardening, give you increased strength and also ductility. That's good part of high entropy alloy. The bad part of entropy alloy is shown here. This is ternary medium range entropy, medium entropy alloy. If you try to harden it by solution, you add lots of aluminum silicon addition. It don't harden but at all, because all as in solution will not give you extra hardening much. So the most important one is by precipitation. Okay, here I show some of our own work. We try produce dense precipitation of narrow scale L12 particle can be readily formed in the. We choose the ternary nickel, cobalt, iron, give you new FCC material, additional aluminum, titanium, put aluminum 2 particles. You can put many of them as shown here, okay, which we treat by high temperature solution by precipitation. This is the grain structure. You can see the precipitates. We can get lots of precipitates. Now, the size of the precipitate is about 30 to 50 nanometer. The volume fraction is 60%, okay, which are all coherent with the matrix. We can easily produce this interesting precipitates in the material. Here it shows the TM diffraction, indicates that the particle are coherent. This particle and matrix are coherent to each other. Okay. Yeah, interesting. For the complex system, you form this precipitates. This is not simple precipitates, very complex precipitates, okay, which is different from nickel-based superalloy, from simple nickel-3 aluminum precipitates. Then show what's the results we can get. This is a binary ternary alloy nickel cobalt ion. If you add all these 60% the nano precipitates, you get the yield stress increase by a factor 5. Look at the ductility. Because of work hardening, the material can deform extensively until you get 50%, then fracture. The ductility even better than the base material. Okay, you look fracture mode, show the dimple fracture. Also, compare with traditional nickel-based superalloy at room temperature. This is strength, there's elongation. Typically, strength increase, decrease of ductility, right? Here is all alloys with yield stress around 1100 MPa, and ductility is 50%, way better than conventional nickel-based superalloy. So we solve this ductility, strength, and improvement problem. Second, show the necking problem, okay? Look at these 2 alloys. These 2 alloys with small difference in composition with the structure of these nano precipitates. Okay. Then you see, the one showed necking, one did not show necking at all, right? In this case, we try to, okay, what can that go? Stop. Don't count the time, please. This is not my problem, right?
It's like the footballer.
Oh, no, fine, okay. We try to understand, okay, why this one show necking and this one doesn't show necking, okay? Look at here. We analyze work hardening behavior, okay, as a strength, okay? This is the blue curve, show necking. Red one does your necking. You can see, compare these 2 regions. Region A, B both show small decrease of work hardening, but the red curve, good one, didn't show a decrease solely. Most important in the after 20% elongation, you look at this red curve. The work hardening rate increase more instead of decrease, compared with the blue curve that lose the hardening and the necking and start right away. Here we show another one, show log plot, which give you close to instantaneously work hardening behavior. You see the blue curve and the red curve. Interesting, okay. For the red curve, they show no decrease in region B, this area, and or increase sharply with deformation, okay. So that's the reason why the red curve show continued deformation without necking. Yang Tao did a lot of TM work trying to identify why material in the region stage C shows such kind of high work hardening. Then we did a study of detail as shown here. In initial deformation, typically you see the dislocation tangling around the 1-1 plane. More 20%, you see the tangling of dislocation. Most important, after 20% elongation, right? You see this is the material very quickly. Form a shear bed, micro bed, which give additional hardening. It give you extra strength, induced hardening, and good ductility. Conclusion: the study of the high entropy alloy with a dense precipitation of nanoscale particles, L2 type, has demonstrated the feasibility for the elimination of all critical issues for the design of advanced structured materials. Thank you for your attention.
The third talk for the structural material was given by Professor Jian, our Vice President of CEU.
Thank you, Professor Huang. So now I start the roadshow of science. So now for the startup, we ask the student to only spend 8 minutes to start. So let's start. So my topic today is the development of a dual-phase super-nano structure material, concept, processing, and applications. So I'm from the Center for Advanced Structure Materials. So Professor C.T. Liu has talked about HEA, and Professor Luca will talk about other material, nanomaterial. But I just observed we are in a very interesting packing order, because 23 years ago, we were together in a ceremony of nomination of the consultant professor of Northwestern Polytechnic University. That started my 20 years collaboration with Professor Lu, and also I know Professor C.T. Liu, and we started collaboration 10 years ago. So this is the outcome of this two major collaboration, because I learned from Professor C.T. Liu about the different type of material, including HEA, and I learned from Professor Luca about the glass and the nanocrystal. So I just want to give you the report of this. So basically, my work is to try to solve the problem of the conflicting property of strength and ductility, and Professor GLEITER gave a very nice talk to introduce that. And so, as you all know, the major problem in the nanomaterial, one is the stability of the material, another is how to solve the reverse Hall patch problem to reach the theoretical limit. So recently, we have found a solution, and I will try to explain what's our scientific achievement. So basically, to achieve the dual property, we should be able to generate strand non-localization mechanism at different scale of the structure. So basically, we try to work on the gradient and the heterogeneity, and that can be generated by chemical way, such as precipitate, chemical composition, multiple phase, and that can also be generated by geometrical heterogeneity, such as topological differences, or physical structure heterogeneity, such as surface, interface, etc. So today, I will mainly talk about the role of chemical composition and multiple phases and interface in this new dual-phase super-nano structure. So this slide summary different work we have done, try to managing the strength and the ductility. So basically, at the macroscopic level, we have developed a multi-layer sheet, steel sheet, or hierarchical microstructure to generate Nicking multiplication. Then we have developed hierarchical nanotwin to generate better deformation capacity, and we work on the metallic glass, try to generate multiple shear band by modifying the structure of the material. To support all this, we have done some simulation work based on the molecular dynamics and finite element method. So 2011, we have found the solution to generate deformation capacity in the material. So we start two works, one in the simulation. So we in that work, we anticipate if we are able to produce two phases of glasses with a difference of 20% mechanical property, then we can generate the multiple shear band in the material. Then we try at the same time to produce such material with a mix of crystal and glass phases. But the major problems with any heat treatment or other treatment, we cannot obtain a very dense combination of glass and crystal. So for this reason, we try to better understand what's happened at the atomic level of this material. So we have developed dynamic micropillar test and fast beta relaxation test try to investigate the heterogeneity in the metallic glass. So at beginning, we have tried to obtain a so-called super-nano structure with the two metallic glass as we have predicted, but we end up with a new structure, so-called super-nano structure, with a nanogram lower than 10 nanometer, and at the interface, it's not the ground boundary, but it's a metallic glass. So why this material is very specific? Because in the old system, we can also obtain the so-called dual structure with phase separation, etc. First of all, there is a size effect. When the crystal is smaller than 10 nanometer, we can difficultly generate dislocation. So where the deformation capacity comes from, that comes from metallic glass part. So for this reason, the mechanical property is totally different. So how to produce this? So basically, we use the PVD to generate the phase separation. So at the heart of this first material, we have modified the power, the target, the composition, etc. We end up with a very interesting structure like this. And in fact, if you look after this, in fact, it's a dual phase, but with a different composition. For the crystal part, we have many, it's a copper-rich phase. And for the amorphous part is magnesium-rich. So the composition is different. For this reason, thermodynamically speaking, they are more stable compared to a uniform metallic material. And in terms of mechanical property, we reach the theoretical limit of the material. So compared to the other magnesium-based material or metallic glass, this new material is with a very high deformation capacity. And based on this, we have developed some new so-called super-nano structure. As the results have not been yet published, I can tell you the material we obtain from magnesium alloy, titanium alloy, and aluminum alloy reach this region with a very high specific strength, super deformation capacity at this region. So to conclude, the strength of the material could be increased by grain refinement. This is a hot-batch relationship with a new deformation flow, with a new interface structure, metallic glass with different chemical composition. The super-nano dual-phase glass crystal structuring solve the reverse hot-batch issue and promote the strength of the material near the theoretical limit. A new family of material was created. I need to stop. Thank you. Thank you.
Thank you very much. And the next talk will be given by Professor Luke of Xiaodong.
Okay, thank you. As we are changing group, I have to start in a different direction. Instead of making alloys as the three previous speakers did, I try to introduce you, is there any possibility to develop high performance materials without too much alloy? As Professor C.T. Liu said, in the past 100,000 years, most materials, especially structured materials, are developed from alloying. But we know the alloying suffers from several drawbacks, including the property trade-off, property saturation, and also the alloy are suffering from resource dependent and the difficulties in recycling, and also, most importantly, the cost keep increasing. Basically, the principle of alloying is to block dislocations, either using single atoms or using different phases or using small particles. The trade-off is very well known as we see in the banana curve. I will show you superalloy, taking superalloys as an example, it's as just the CT introduced. This is a typical nickel-based superalloy. It's very simple. It's FCC structure. From lattice structure, it's very simple. But from chemical compositions, it's very, very complicated. I don't know if you can count so many elements. I cannot. At least 30 elements has been added. I basically come back to look at the element table, periodical table. Here is nickel. And if you put all those elements in, you will see a simple superalloy basically contains those elements which occupy most of this periodical table. What is more, and if you count, count the property enhancement over the past decades, you will see the property gradually increases, but the incremental rates become smaller and smaller. But at the same time, you can see the cost keep increasing very sharply, especially when the property getting slowly increased. So this is the reason we have to rethink about how far can we go with this kind of alloy. Is there any alternative? So there is an alternative. Blacksmith is the best alternative. We know everybody sitting here know blacksmith is a very simple approach. Is simply hammer the metals and the property will be changed. Also, the blacksmith's principle is also very simple. Block dislocation, either using dislocation themselves or using the grain boundary. And however, there is also limitation. The first one is still property trade-off, and the second is a property limitation. And the reason for that is those kinds of, the blacksmith method is basically pumping defects. Stability of defects will be a bottleneck. When you pump in so many defects, the defects become unstable. So this is the limit. Can we stabilize? And I think the ultimate state of pumping defects is the idea proposed more than 30 years ago by Herbert GLEITER, that we can produce this kind of extremely fine grains so that the grain boundary population is extremely high. However, with this increase of strength, population of boundary, strength jump up, the ductility drops, thermostability drops. Over the past 20 years, I think we already find out some solution to stabilize this kind of structure, either using this by tailoring structure and the composition. We find you can use low energy interfaces to stabilize this nanostructure, or you can use grain boundary segregation to increase kinetic stability. As I mentioned early this morning, I will skip over using this either nano twin structure or low angle grain boundary, which is both are low energy interfaces. Also, you can using the grain boundary relaxation processes. Once the grain size becomes smaller enough, the grain boundary will autonomously relax themselves so that the structure will be stable. Okay. And also you can change the spatial distribution of the interfaces that can give you a chance to delocalize strengths that can increase ductility. With all this information, all these progresses, we believe that we already find a way to stabilize those defects. Then we should come back if we can, using all these stabilization approaches to develop high-performance materials so that we can make some materials plan. I mean, we can use metals without, even with less or without alloy. So we proposed this idea 2 years ago. Means if we can play these defects in the right way, we may change the property of this pure metal or slightly alloy metal like IF steel which is very soft but ductile. You can make it very strong and brittle, but in between you have a very large envelope. This envelope is large enough to cover many of these steers, different type of steers. So if this can be done, the manufacturing process will be significantly changed. Because earlier, if you want to set up, produce a set of parts, you have to use a different alloy from metallurgy, starting from a different metallurgy source, all the way to different shape, different property. But now you can use tailoring these properties. You may have a chance to prepare from one alloy, one kind of materials by changing the property, only by playing the defects. So I think we do have a chance to enhance property and performance of metals without too much alloy. At least we can reduce the alloy elements, especially for those hazard procedures and also skillful elements. So I think we have many challenges. I think it's time for me to stop here.
Thank you very much. So the next speaker will be given by Professor Robert Ritchie from Berkeley.
Thank you. Well, thank you. I feel when we're talking about properties, we're talking a little bit more about engineering here. So damage tolerance to me is the ultimate engineering property for a structural material. So I want to just focus on that. We all know, we've heard all this today and during this conference, what is damage tolerance? And it's, of course, a combination of strength and ductility, but it's more than that. It's toughness as well, which is the combination of strength and ductility. Issues with this, we talk about structural materials. I think one thing that one has to remember is that the timeline between designing a new structural material, which we've heard in this conference, and its actual use in a real live application, I mean a real one, not a new skateboard or a tennis racket, takes decades. Unlike electronic materials, where you can happen in almost a few months these days, but perhaps a year. We've made plastic airframes now out of polymer composites, which were first developed 30 or 40 years ago, and the same thing is true for ceramic composites. So there is a long timeline we have to deal with here. So this is what I think is the biggest structural material breakthrough in the last 50 years, and this has been the development of ceramic composites. Professor Lou could make fun of superalloys, but this is what's replacing superalloys. And these are now being used in GE's engines, not in critical parts. They're gradually coming from the cooler part of the engine forward. But these materials are, I think, extremely impressive. Typically, they're silicon carbide materials. This is a materials summit. This is the first non-metal you've heard today. Reinforced with itself, reinforced with a silicon fiber. And the notion is the same, strength and ductility. The silicon carbide's strong, but it'll be brittle and it would break catastrophically, but it has an R curve because the fibers hold the material together. And it gives it apparent ductility. It means that there's a parachute. There's time before the thing breaks catastrophically. You can see failure. So I think this is, personally, the biggest alloy design breakthrough. And there's a lot more to do with this. These things are lighter than nickel. They can run many, many hundreds of degrees hotter than nickel. But they suffer from a whole range of different corrosion problems, quite frankly. So that's where the activity will be, I think. So what's new in structural materials? Well, the first thing I think that we haven't talked about today is the notion of bioinspiration. What is nature? How does nature deal with these things? A lot of the materials you've seen this week may not have been inspired by nature, but they could have been. Nature is rather adept at combining what I call intrinsic and extrinsic toughening. So what's unique about nature? Nature has two things that I think which are particularly unique, and the one that everybody knows about, of course. Oh, sorry, I'm using this badly. Oh, this doesn't like my talk at all. It of course produces hierarchical structures, and you've heard that name mentioned by Professor Liu and others who've been making steels that way. But the second thing that is very important about nature is it generates gradients, and you've heard that in steel technologies today. So how does nature do it? Well, you know, the human tooth, for example, is a beautiful example where you'd have a hard surface, enamel, which is primarily a mineral, and yet below it there has to be a tough underbelly to stop the tooth breaking in two, and you add collagen. But look at the interfaces. They're all very, very graded. They're never sharp interfaces. There's not necessarily a singularity that could cause fracture problems. In other examples, this is a horse hoof, and now we have a gradient in the size of the structure, just like a grain size gradient that we've seen here in this conference. Only now it's the size of the tubules. We have a very hard surface here and much more ductile in the middle. But there's also a change in the humidity that's generated by these different sized pores. We don't generate, of course, that in metallic materials or structural materials yet. And the one of my favorite is the Mantis Shrimp, which is a shrimp about the size of a piece of chalk, and yet it has a club that can break aquarium glass, literally break aquarium glass. And this is a really remarkable structure, which is called a Boulegan structure, which is like a spiral staircase. A lot of fish scales have this too. How do you simulate that? How do you make that into metal? It's a very effective structure. From a brittle point of view, it makes cracks go through a helical structure, which is deflection, and that you could probably simulate. But in the ductile version of this, which is seen in a lot of fish scales, the collagen, which is what we're showing these fibers here, actually will rotate to carry more of the load. And that's a smart structure, which maybe we'll be able to simulate, maybe we won't, but it's certainly a very, very effective structure. Your skin's the same. It's impossible to tear your skin because the collagen will rotate and unravel and do lots of processes like that which are energy absorbing. So the issue here is can we utilize this? Well, a lot of nature's approach is bottom up, and we don't do a lot of processing from bottom. We don't do it at the molecular scale. So perhaps things like 3D printing, if it ever generates structures of the properties we can control rather than just a shape, may do that. But what's encouraging is that a lot of the work you've heard in this particular meeting has been associated with hierarchical structures. You've heard those names this afternoon, and with gradient structures. A lot of examples of that. So I think without the need for bottom-up molecular design, which is very, very difficult, we're seeing a lot of nature's rules and strategies applying already. Just to finish on that, I think the things that I find most exciting in structural materials these days are these kind of technologies. The things we've heard about with respect to steels, the things we've heard about with respect to gradients and the nanostrength thing, all really either inspired or copying or the same as how nature would approach these things. And of course, high entropy alloys, as CT mentioned, is an unbridled future. There are 50 elements in the usual elements in the periodic table. If we look at just 5-element alloys, there's 44 million potential alloys out there. If you start changing composition slightly, there's an unbounded number of alloys. How we actually probe that vast universe is another challenge, but certainly I think this area will see a lot more potential in terms of new engineering materials in the future. Thank you.
The next talk given by Professor David SROLOVITZ. I think from this week he becomes the head of the department in CTU. So he's the CTU guys.
Okay, so I took a little different tack today. So what I'm going to try to describe to you is trying to focus on the interaction between microstructure and mechanics, but I'm going to try to do it on the mechanistic level and try to show you how some of these things interact together. So let me begin by showing you, I'll let this play, I hope, while I go on. When we usually think about microstructure, we think about mechanics, we usually think in a reductive sort of way. We usually think about very basic things. We think about how do grain boundaries move, how do dislocations interact with grain boundaries, and we have nice little models for each of these things. So for example, if we look at grain growth, classical problem, you just say the velocity is proportional to curvature, integrate. And you have some interesting additional things. Let's see if I can make this play. So this is just one grain out from the middle of there. So this is a very simple idea of how the microstructure evolves. And the point I would like to make today is that if we look at each of these individual phenomena in isolation, we're missing some very important interactions between them, which I think has a lot of possibilities for the future. So I just put up these 3 examples. This is just classic curvature-driven growth. This is Hall patch strengthening, and this is grain boundary sliding. All classic mechanisms. Now what I want to do is walk away from the simple ideas and try to do something, trying to actually just sit back and watch to see what happens. So this is a molecular dynamics simulation of a nanocrystalline material, and all the grain boundaries you see moving there are moving just basically under the effect of their curvature, just like the picture I showed you in the beginning. But what you actually see going on is it's generating twins. It's spitting out dislocations. It's spitting out point defects. There's no stress applied. But if you look at all these things, the kind of twinning you're getting is basically mechanical twinning. And the dislocations that are being spit out are being spit out because you generate stress when the grain boundaries move. And because of that, you have all sorts of interesting interactions between these things. So if I just take one snapshot out of the whole thing, so you see these are the grain boundaries, you can see twins, you can see steps. So this is spitting out an array of twin boundaries, parallel twin boundaries. There are dislocations in here with stacking faults, interactions between them. And all this is happening without any applied stress. Okay? So the point I'd like to make is that microstructure evolution is intrinsically a stress-generating phenomenon. Now we can turn the question around and say, well, if I apply stress, how does this affect how the microstructure evolves? And we'll try to play the same game from the other side. And basically, so what I'm trying to show you so far is the deformation and polycrystal evolution are explicitly linked. And the link between those basically comes down to the way grain boundaries actually move in materials. And the way they move is through this missing link, which are line defects called disconnections. Disconnections are line defects. They're completely determined by the bicrystallography of the problem. And the bicrystallography tells us that these defects are line defects. So here's a grain boundary. It's a line defect coming out like this. It's characterized both by a Berger's vector and a step height. And crystallography tells us exactly what those can be. It doesn't tell us which one it is. And so what I'm just showing here is a combination of different Berger's vectors, indicated by the first number, and step heights here. So for example, you can see here something with the same dislocation character, but 2 different step heights. And if you actually look at the stress fields associated with them, you can see that they have exactly the same stress field because they have the same Berger's vector, but different step heights. Now, the way grain boundaries are going to migrate is if this thing moves along this direction, the grain boundary shifts up. Okay? So moving these disconnections, these line defects, give us a way of translating the grain boundaries, but also tell us how stress is coupled. Since these things have Berger's vectors, applying the stress drives the motion of those defects. And that by necessity gives you grain boundary migration, because the Berger's vector is driven by the stress, and the Berger's vector carries along a step with it. Okay, so here's a classic movie from Kahn and Suzuki, Kahn, Mission and Suzuki. So what they're doing is they take a bicrystal, shown here, they draw a fiducial mark, they shear it at a fixed rate, and you can see while they're shearing it like this, you can see the grain boundaries migrating down because you apply the stress. If I apply the strain rate in the opposite direction, the grain boundary moves the opposite way. Okay, so there's a coupling between microstructure evolution and grain boundary migration. So this is a movie from my friend Marc Legros. It's some TBM image. So this is a thin film of aluminum, it's ultra-fine grain aluminum. What I'm pointing out is these are the grain boundaries here and here. And you can see as this boundary is migrating this way, you see all these defects marching along there. Those are those disconnection lines. So A, I'm not making it up. Okay, so let's go on. Now, the interesting thing here is if I was going to force the grain boundary to move, I say, for example, saying there's a jump in chemical potential across the grain boundary, this grain boundary that's here starts to move up, and the two grains then slide relative to each other as it moves up. And the ratio, so that slope there, is just the ratio of the Burgers vector to the step height. And it completely you can determine it crystallographically. And for this particular grain boundary, the value is about 0.6. Now, here's another interesting thing. What I'm going to do is still drive the grain boundary up, but instead of leaving the ends of my sample free, I'm going to hold them fixed. So if the grain boundary moves up, it wants to shear over, but you're going to generate a back stress. If you generate a back stress, the grain boundary, exactly the same one, migrates from here and then stops after a very short distance. That's because the stress counterbalances the chemical potential driving force, and the whole thing's cancel. And so if I look at the shear stress in the material, the shear stress shown here starts at 0 and goes to some finite value and it gets fixed and then stops. The grain boundary migrates some finite distance and stops. Now, I'm going to repeat this with another grain boundary that's shown here. So this is the same kind of simulation as this, fixed ends, but here, this particular grain boundary, as it migrates up, it migrates here where it should stop, but instead of stopping, it's shearing this way, and then all of a sudden, at a certain point, it starts shearing back the other way. The boundaries still migrate in the same direction. So what that tells us is that the Burgers vector is now the opposite side. And so you can see, you get this zigzag here. And so for a grain boundary to move, it's shearing it, unshearing it, shearing it, unshearing it. Okay. And then, if you apply the same ideas to a real microstructure, what you can see is that some grains will shrink and disappear, these square ones, and other ones should shrink and disappear, but they don't. The reason is that some of them can operate different mechanisms and that allow it to shear and shrink by operating plus and minus disconnections, and the other ones do not. And the ones that do that also have a big rotation of the grain that goes along with it. So all these things are related, and if I had another hour, I'll tell you more. So thank you for your time.
Thank you very much. Okay, yeah, for the functional material, the first talk given by Professor Chen Lih-Juann, the former president of National Team Park University in Taiwan.
Thank you, Professor Huang. As material scientist, plasmonic property are not most common property we look at, but plasmon-related phenomena have received a great deal of attention in recent years, and for the SGI paper, there were 75,000 papers published in this field in the past 25 years. In particular, with the coin of plasmonics, the name, there were a lot of papers published from year 2004 and on, and there were about 5,000 papers published in the past 2 years, each year. And plasmonic property is induced by the coupling of electromagnetic field with the collective motion of free electron near the metallic surfaces. And from electromagnetics, the matching of the boundary condition requires a thin dielectric film, or it is advantage to have a thin dielectric film. So if we look at the field, the main work are still in material science as well as in photonics. And I personally bumped into this field by working with a group in our University of Physics Department group, and we work on the nano laser, and subsequently we work on the optical circuit, as well as the application in energy and the environment, and the detector for chemicals. And for Plasmonic, it has the advantage of high speed and miniature size compared to other possibilities. And this is a paper we published in 2012. It's from the tiniest nano laser at that time. And it's become possible because of the high quality epitaxial metal film. It's a thin film, it's a single crystal and defect free, and also high quality dielectric film, and MB glow source. It's an indium gallium nitride, and it also, the structure is well controlled. And subsequently, by varying the compositions, we can change the color. So it's become a full color plasmonic nano laser. In our recent work, we start work on the room temperature ultraviolet nano laser. It uses the zinc oxide nanowire on a single crystal alumina film. Zinc oxide has a nice property of lasing at room temperature, the UV room temperature, and it shows ultra low threshold field. And it's possible, again, because we have single crystal alumina film grown on alumina sulfide. And this is a characterization of the single crystal alumina film. And it shows a very low threshold compared to the previous work. And it's consistent with the simulation result with the thin dielectric layer. But close look at the interface, it shows a native oxide of 3 nanometer. Therefore, it's become puzzling why it's why the 5 nanometer ALD deposit alumina film gives the lowest threshold. And close look at the interface, it shows ALD grown alumina film have stoichiometry, have a right stoichiometry and with this defect. And also it's from AFM, it's more uniform, it's flat. And so recently we also work on other high dielectric film that is have a stronger coupling, have even lower threshold. And for our work, other work, we have made a nano antenna out of nanosphere array, and we have a special way of arrange the nanosphere so that it can be wavelength selective In some case, it's more sensitive in wave of green color, and some it's more sensitive to red color. So it's a nice nano antenna. And we also use this phenomenon to enhance the hydrogen production. Again, with the nanosphere array, but with the ALD deposit, titanium oxide thin layer, and with different thickness. And it's particularly effective with the regularity that we have highest hydrogen production rate. And similarly, we have metal attached to a semiconductor and use the plasmonic property to make the enhanced production. And this is a work on solar energy. And the solar energy using the plasmonic enhancement, again, of the to enhance the absorption of the light, and it's embedded metal inside the zinc oxide crystals, and so that it can avoid the corrosion problem, and with appropriate thickness, and we can have the strong photocatalytic properties, and this for environmental protections. We have again, we can have very tiny nanoparticle on the semiconductor, and it shows the enhanced photocatalytic property. And this is the area which has a commercialized applications. That is, we can detect the small number of chemicals, intermediate. And this area in biological area, and it turns out it's a relatively useful area. That is, it has a real practical application, but the plasmonic property at this moment has no big industry behind the whole field. But stand out is biological application. Thank you.
Thank you very much. The next talk will be by Professor Xiaodong from Shenzhen. He's the initiator and inventor of Materials Genome project.
I would like to talk about material genome scientific infrastructures we have in Shenzhen, as leading by Southside. First of all, I believe we're having a lot of new things recently. It seems to me that after this book by James Gray, that many areas of science entered into a new era. We call it a fourth paradigm. Basically, very common in different world. We all talk about AIs. But it turns out the biggest AI that we are now looking at is in material science. After 2011, especially in the last couple of years ago, this paper that weakened us. So we're into really a new age of data plus AIs. For example, a lot of physicists were surprised that machine can learn things that we cannot imagine. This basically predict a much higher cure temperature by learning just the field data here. However, in order for this to really happen in our daily R&Ds, we really need a lot of more data. In material science, what we call it data is basically underlying relationship between these four factors. Basically, composition, structures, and thermodynamic parameters, and the physical properties here. So we basically call this as a material genome, basically a big database. However, in material science, we have very few data. We realize that even we just deal with a 4-element chosen from periodic table, that we need our data, basically 1 trillion data. What we really have now is about 1 million. Okay, so we're far away from have enough data. And this project we have basically we call it Genome Project. Material Genome Project is basically a technology by increasing the speed of our data collections and then learn how to analyze them. So we have an we have basically had a funding about $1 billion yuan here that we're building user facilities, trying to speed up our data collection and also calculation. So basically, high throughput experimental facilities and also high throughput calculations in order to help us to increase the data collections. And I would just give you a few examples and give you a flavor. I don't have enough time to go through all these capabilities, and just give you a flavor how what we can have in there. Basically, we have a high throughput composition platforms that we call it. There's 1-dimensional material chips, 2-dimensional thin film material chips, and 3-dimensional structure. Basically, in order to have a variation in many components, we have continuous varying metal fibers, or called metal ribbons, and also basically this organic fibers in here. So we have high temperature metals, and we also can make 2-dimensional material chips and 3-dimensional high surface area material, like basically in here. We can also make chips in the electromechanical ways, having different material testing and properties. But especially what more difficult is how to characterize them, so many components. So we call high throughput characterization platforms. Basically here that we're trying to measure in micron size, in situ, in real time, very fast speed, and as much as physical properties we have. We at least can measure up to 15 different parameters in the same time, all in one facilities. Okay. Give you an example. For example, most important one we have in the X-ray diffraction, we can measure crystal structures and compositions. In here, we used to have, in order to obtain this lattice parameter, we usually either vary the theta or lambda. But here, we managed a method that we can measure both at the same time, increasing the sensitivity of measuring a polycrystalline samples, a very small mass, up to 10,000 factors speed. After this, we have a laboratory-based facility that we can measure a very small sample, just 100 nanometer thick, thin film, about a few tenths of a micron, very small mass that we can measure in the faster than synchrotrons. And if we use synchrotrons in the same factor, we can basically measure this by highest speed in the synchrotron right now. And if we use the same energy-sensitive array, that we can turn a synchrotron much faster. So basically, we can measure in the real-time structure change. And next one is how about physical property? Can we use optical method to really fast, very fast speed to measure a conductivity, for example? It's very difficult. After Dude discussed his model about 100 years ago, more than 100 years ago, we really don't know until now that we can use an optical method to measure resistivity. But turns out in the Dude model, there is theoretically this conductivity parameter, basically the free electron scatter with the phonons. This gamma factor is in there. So from the paper, you can measure it. Why you cannot measure it? We found out basically optical properties, the metal surface, because this optical field only enter into metal only a few nanometers. Big surface impurity affected. So we basically choose a frequency at a plasma frequency. So we just heard about plasma. But this is the bulk plasma frequency of metals. You measure at that frequency and modulate it with the temperature that this blue curve shows. Basically, if you do measure this way, you can basically get rid of all other interference in the on the surface. Experimentally, we proved that it's very effective, so we can measure it very nicely. Okay, we finished. And we can also measure parallel, and with a single crystal, large crystal parallel, every pixel we can measure a rocking curve. Basically, we can measure a large single crystal growth of about 1 million or 10, or even higher pixel in a couple minutes. Parallel measure the image of the crystal growth. Thank you very much.
Thank you. The next talk will be given by Alice and our Provost and Vice President.
Okay, thank you, Jacob. So last night I was joking with Professor C.T. Liu, okay, talking about I'm going to use 8 minutes to convince you, right? You know, we are going to solve all the clean energy needs, okay, through some of the printable solar cells. So I'm going to do the sales pitch in 8 minutes. So, you know, we all know by 2050, okay, our energy needs is going to be double from 15 kilowatt to 30 kilowatt. So this is very daunting challenges. How are you going to find, you know, needed energy sources without really damage all the environment, right? So if you talking about global energy needs, then if you consider all the renewable energy source, talking about wind, biomass, hydro, geothermal, and also you're talking about all the non-renewable sources, natural gas, petroleum, everything in there, right? And this the size, the circle, is talking about capacity, right? So the solar energy is one of the most abundant energy source. You can tap into that and can produce some clean energy in that. So this is talking about annual of the sunlight you can harvest to generate potentially solar energy in that. So this is a tremendous, right? Okay, potential in there. But then if you look at the solar cell development in the past about 40 years, right? And the price to generate per watt is a change from about more than $100. Now is about 37 cents, right? So, but then you said this is several order decrease of the cost. How come? Not every household have a solar cell on top of their roof, okay? In order to really produce clean energy and preserve the environment. Because, you know, the material cost is considered is only still relatively small part of the solar cell infrastructure. You still need to have all the rack, all the converter, all the different infrastructure in order to connect in that, right? So that accounts about 80% of the cost. So then this is a new story I'm going to tell you, right? This is talking about the new discovery of the hybrid perovskite-based solar cell technology compared to all the, you know, the current technology, solar technology developed, for example, silicon-based solar cell developed for 40 years or so, right? And if you look at, you know, the perovskite solar cell in the from the 2009, in less than 9 years, the power conversion efficiency changed from about 3.9% to now about 22.7%. Okay, it's very close to that of the silicon-based solar cell. And compared to make the silicon solar cell needed about 1500 degrees C of the temperature and the batch by batch silicon wafer process. This, you can just simply mix the lead halide and also ammonium halide together and the process at low temperature around 100 degrees C and print it as a thin film. As simple like that, right? So that's the reason why in few years and the efficiency being so attractive and the material is almost ideal semiconductors with all the light absorption, mobility, and also their binding energy also very small. So when you shine light immediately, they separate into absorb photon, separate into free charge carriers. Okay, so all those wonderful properties produce, that very rapid development. Professor Chen talking about Plasmonic's importance. Just in this half year, right? June even haven't finished yet. It's already more than 4,000 papers published in the postgrad solar cell field. Means this field is extremely competitive. But then, why is this besides the efficiency and all the promise? If you look at very important factor called energy payback time, right? Means the energy needed in order to manufacture the solar cell, right? So if you look at silicon-based solar cell, take about 13.5 months to recover the energy you put in to make the solar cell. But if you look at postgrad solar cell, it's about 1/10 of that. Means you can very quickly recover the energy you put in. That's the reason why, if you look at from all the way from the top scientific journals to all the way from Europe, talking about China, talking about America, all view this as a potential game changer in renewable energy, right? Because that can be very easily made and can print it in solar cell. So if you look at that, the promise of this solar cell technology is just like you have a precursor solution and you can print it just like you print a newspaper, and imagine how fast can you print the newspaper, right? And this is a way you can really address the scalability issue instead of batch to batch in a semiconductor in the clean room trying to process your silicon-based solar cell in that. And also, it's very easily to tune the material properties, so you can either make a large gap material, you can make a small gap material, then you can stack on top of each other to make a tandem cell out of that to absorb even more light, right? And also, you can have a versatile form factors. So you can print it, make it as light as a piece of paper. So, the mounting, all the infrastructure, and also potential application, even used for window application, can be relatively versatile. So you can look at one of the very attractive application is used as a solar window application, right? Because the perovskite solar cell can be made in a semi-transparent, okay? So when you buy a car, when you want to have a privacy, you say, I want to have tinted window. This is ideal for your transparent solar cell. And imagine all the high rise in Hong Kong, okay? With window, all can become, this is a semi-transparent solar cell window, silently harvest sunlight to generate energy. Okay, this is a totally different compared to all our previous ideas. All the solar cells need to be put on the top of the roof in order to really collect that. So you can utilize that. And this, if you look at that, this is a semi-transparent solar cell made by my group. Okay, then put it in front of these roses. Can you see the difference? Actually, it's exactly just like you look through the tint window. Okay, and this is almost ideal for all the car you drive. All the window you are using, you can all potentially explore this. So, unlike all the distinguished scientists just present their talk and a lot of data, I only have one or two, right? Because I figure this is a very general populace, right? So, if you look at two of the very challenging topics we have to address, one is talking about stability, okay, and long-term stability. And if you look at the result we got, you can get a very high power conversion efficiency. But also, you can see the stability we already test is more than 14 months continuously, okay, in that. So this has already show the promise for potential commercialization. And also, people say, okay, lead is not good, right? Besides lead, we can use all kinds of encapsulation methods, and also use maybe protecting layer like EDTA to capture any potential leak lead ion, right? But if you look at how about we can change the UL property by composition engineering, through the years, we have changed from 15, 25 to 50% and complete replace that with lead, with a tin, okay? You can get all of that achieved, okay? So this shows you the diversity of the the composition engineering to really do that. And also the promise of this technology is you can use to combine, to be combined with current technology. Okay, just 1 minute. Okay, so speed it up. Okay, so you can make a tandem cell, and then if you look at that, the tandem cell we are making is already can also approach that of a silicon solar cell, right? So this is very promising. So in order to take into consideration of this technology, you need to simultaneously take care scalability. Okay, so that's what we are doing right now. Instead of making small size device, how do you make large size device? Durability, sustainability, and take into account the whole eco property. So when you start talking about printable solar cell, it can be used for all the wearable electronics you are trying to use. With the portable power source, you can use a built-in integration, and also if I couple that, just print one layer on top of the existing silicon solar cell, I can enhance efficiency of the existing solar cell also. So I can make it above 30% power conversion efficiency to really use that for solar farm and also electricity generation. Thank you very much.
Very exciting. So the last talk, we are doing so well for the timing. Yeah, we're given by Professor Ken Leung from Columbia University.
Dr. Huang asked me to give an 8-minute speech on the future of biomaterials. I thought that would be pompous for me to say that, to do that. So let me share with you some of the promising directions of biomaterials research, and I'm sure I would have missed many others. Biomaterials have evolved from serving a totally inert to a supportive role to more an active role. Increasingly, the biomaterials are multifunctional, integrating with other disciplines and also inspired by nature. So one aspect is that the biomaterials will serve a therapeutic function. When cells die or activated, they release danger signals into the body that will activate the immune cells to cause inflammation. Many of these danger signals are nucleic acid in nature. So we have designed cationic biomaterials to scavenge this pathogenic nucleic acid and show that it could achieve a therapeutic function in treating rheumatoid arthritis. So, and this can be done in different configuration. So the message is that this is no longer a passive carrier to deliver drugs or genes. The carrier itself could have a therapeutic function. And more biomaterials design will try to do that. Many biomaterials are now designed to activate or to inhibit the immune response for various purposes. One example is that when mast cells, during infection, the mast cells are activated. They would shed these submicron particles that are rich in heparin and various cytokines. They would travel to the lymph node to activate the immune response. So to mimic that, we use chitosan to complex heparin by charge interaction, forming nanoparticles and trapping cytokines. And these cytokines would travel to the lymph node, which is the epicenter of the immune response generation, and show that this nanoparticulate adjuvant could protect animals from a lethal flu challenge in a way as good as the gold standard in the field. We all know the power of regenerative medicine. At the center of it is the right target cells. In getting the right cells, biomaterials can play a significant role to help generate these cells, to direct the differentiation of stem cells to the right cells, or directly reprogram adult cells from one lineage to another lineage. For example, they could help deliver the right elements to reprogram the cells. Or in the culturing of these cells, the biomaterials can provide the right cue to promote that process. For example, stem cells culture on a graphene-coated surface would have enhanced differentiation into the neuronal lineage. This exciting development of the marriage of biomaterials with electronics. I just highlight the work of two of the leaders in the field. Charles Lieber at Harvard has designed this injectable microarray, showing that they could be folded, injected through a needle to the brain, then they unfold, and so this could be used to stimulate the tissue or serve to measure the electrophysiology of the tissue. John Rogers at Northwestern has developed a wide range of these polymers materials in different formats that could be applied for a range of medical applications. One example is shown in here, that this is a flexible microfluidic device that could be attached to the skin and could measure the parameters in the sweat of the wearer, such as glucose level, pH level, temperature, and so on. So there are many exciting things that one can do. So lastly, cells are very sensitive to the substrate to which they adhere. Biomaterials development till now have been quite empirical. You want to optimize the application with certain cell types. Increasingly for the future, there would be a more rational manner. For example, the marriage with combinatorial science, one could use monomers with different properties, different charge, hydrophobicity, hydrophilicity. Then they could form a wide range of substrate, and then leveraging with the power of the omics era, one could get the proteomic as well as the transcriptomic data when cells culture on this wide range of substrates, get the data, and this would generate a huge data set, so there will be a whole range of computational approach that could be applied toward this combinatorial material discovery and optimization. So I think those are some of the promising biomaterials research areas that would advance the field. Thank you.
So can we just give a big hand to all these 10 speakers there? It's extremely difficult for the professor to give a talk within 8 minutes, I know. Yeah. Usually it's 80 minutes is probably more appropriate. Yeah. So I'm sure all the speakers have a lot of questions to the other party or something. So now we have a panel discussion. First, let's concentrate on the structural material first. Do you have any question for the structural material aspect, including the performance part? So now we open for the Q&A.
Can the panel ask a question?
Sure.
Can I ask a question to Dr. Jian about the materials genome? Is this concept going to be very useful for structural materials, do you think?
Yes.
How?
How? For example, if we are looking at high entropy alloys, so you can directly build material chips that covers a large phase space. That then you use different imaging, different characterization method to find what you want. So basically, you in any area of material, you basically increase the data collection rate.
Well, the problem I have with this, if we're talking about electronic materials, I would buy that. But if you're talking about structural materials, you're dealing with microstructure.
Yeah, you can image the microstructure directly. So you can fast speed imaging them over a decade of different scale.
But it's very difficult for us to look at a microstructure and know properties. So I mean, to me, a lot of these materials genome approaches would miss steels. You'd look at iron and carbon and say, what's the big deal? Because everything's microstructure, metastable microstructure. We're always criticized because we do it by trial and error. We add a dab of this and add a dab of that. But it's very difficult to see how you can do it in a more profound fashion. And I think high entropy alloys really brings it to the fore.
Yeah, for example, we heard the talk today that we have 30 elements in there. In doing each experiment, you need to make a big parts, and you need to make basically a billion experiment to find that. That takes 100 years. However, what you really need to know is each element, what did they do? So by this, you can do it on the microchip. You can do it very easily. And doing 10 to the 8th experiment on the chip.
So what experiment would you do?
What exactly experiment?
What high throughput experiment would you do?
For example, if you do a different element, so we make a fibers, continually add varying different element in there, even a small part, maybe 1 part per million. You can just add it to it like a film, like a movie film. You just play them, measure the mechanical properties at the same time when you vary the compositions.
Those properties would be dependent on microstructure, which would not be real in that little thin film.
But the microstructure is made either you can control the microstructures, right? By different methods.
In a thin wire, or in a little thin dot, and if you do it by combinatorial, you'll look at little dots of metal, little balls. And what can you measure? Can you measure the toughness from that?
Or you can do imaging, right? Like X-ray imaging.
But you still can't measure the mechanical properties.
We do atomic fine structure.
But what does that tell you about the mechanical properties?
You measure, you stress them, right? You pull them, right? When you play them, you pull them. You measure the strength and the modulars.
But then you're back to the normal way of doing it. You're taking material and doing experiments.
Well, this is basically you're changing material composition continuously.
But it's not just the composition; it's the microstructure.
Yeah,
and that's
you can always find a way that you cannot do, but if you can do better, why not do better? Why not do faster?
I hear you. But I don't know how you do it for mechanical properties where you're dependent upon microstructure. And if you look at a little dot of material, you won't reflect the microstructure in a larger part. It's a very tricky problem.
You always think that we doing science in in physics, for example, we can image atoms. Why not the defect? Defect is in the microns. So we're talking about micro and mesoscopic and microscopic. We have in physical property measurement, we have technology that we can do everything that you cannot imagine. So if we stay in our own field, they say, well, we cannot do that. We always do this way. You might go back 2,000 years. Now we have technology that we can do a lot of things differently. Yeah, it is. But just me say, I am. Just a few words, okay? I am from Berkeley. Yeah. At the time I invented this technology, a lot of people hate this, okay? And say, okay, you basically destroy the future of my job. You're grabbing all my jobs. So I have a lot of questions in this. Now there's nobody asking this question. In biological science, nobody asking why you cannot. Now we can cure cancer because of what? A genome project.
But that's not the rationale behind my question. My question is the feasibility of doing it.
There's a lot of science.
There's a lot of words you say, but the reality is much more difficult. Much more difficult.
Any other question for the other subject? Yeah.
Very simple question. About the solar cell thing, it was very convincing. So why are not people using it today already? Because that would solve all these energy problems. It's a naive question.
So, okay, so this is the last two slides I show, right? Okay, because it's only take about less than maybe 5 or 8 years, right? To from almost we don't understand anything about the hybrid perovskite solar cell to now really have a lot of understanding about the perovskite solar cell. But still, now you can make the small scale solar cell, the small size, right? Okay, and the small size, if I say I can make it into say 1 centimeter square size, compared say I want to print 1 meter size solar cell. That's a lot of difference because when you start to change the size, for example, then your morphology change. Your solvent, all the different crystalline process also change in that. Okay, so a lot of the process you need to unknown in order to solve those challenges. Or step to re-implement those into your practical process in that. So if you consider silicon solar cell, right? Why does it? The semiconductor of silicon have been known for many years, right? Okay. Take about 40, 50 years in order to take that all the way to Jacob field, the last few percent of the power conversion efficiency. Because you really need to understand all the detail in order to solve the problem, okay? But compared to all the other semiconductors, this is, I think, the rapidest development, okay? In less than 10 years, you already almost reached all the commercialization efficiency, okay? With all the also other combined properties. Because you are not just to focus on efficiency, but stability, photochemical stability, environmental stability, everything you need to take into consideration, okay? And also processability, for example, right? People will say, okay, if you print out a large-scale lead-containing perovskite solar cell, so would that damage the environment, right? Okay, so then you have to come up with a way to potentially seal, encapsulate your solar cell, but also try to maybe come up with a clever way to capture any potential leakage of the lead ion into that. So that is the current the focus right now, right? To really optimize all the surrounding parameters in order to really commercialize this. Yeah.
So many people work on this area, right? And so many papers published. Do you think? Yeah, of course, you. Interesting question is that you think it take how long? Rare, so by you called the printable perovskite solar cell can be used. How long you think from now? You think with all these efforts?
Okay, I can paint you a very promising picture in this, right? This is a research and also the development actually are moving simultaneously, right? If you look at, just cross the border to Hong Kong, all the Guangdong area is one of the best place to do all the printing technology, right? They're printing label, printing all the commercial, consumer products. And a lot of, company sponsored by the Chinese government already also getting into this field. Now, if you cross the border in the Guangdong area, people can already print 1 meter square panel, okay, and testing that under the sun and testing all the environmental stability right now. So I think this is a extremely rapidly developed area. One of the key in this area is the simplicity, right? Okay, if you look at, you just have a lead halide, and then you can have any either metal halide or the organic halide. Mix them together in the solvent, and just print it out. That's done. Okay, you already have a perovskite solar cell, and depends on the composition you put it into there, then they will give you corresponding property out of that. So that is the promise, and also simplicity. Okay, is one of the key. Okay, to enable this. If you look at all the other things related to organic solar cell or all the other polymer solar cell or dye-sensitized solar cell, they only taking a lot of time to make a dye, to make the polymer in order to really scale it up, right? Now, this is, you can make tons of this thing in a relatively straightforward way, okay?
Any other question? Yes.
I'm changing topic a little bit. So throughout this conference, I listened to quite a few talks, and also at this summit, we heard about the Materials Genome, which predicates on changing the composition. You make a different kind of materials. And Professor Luca gave a talk on how do you use, just one simple material, you change the microstructure. You can also tune the properties. And if you combine these two together, as I think about high entropy alloys, I mean, that's a magical material. This touches on both the very complex chemistry as well as you have a very, you can have all kinds of microstructures, and this gives you the multitude of parameters you can work with to tune the material's properties. So to me, this I'm really very excited about high entropy materials now, because now you have lots of parameters you can tune to really tailor the mechanical behavior just from mechanical structural materials aspect.
Is it a comment or a question? Yes. Do you need anybody to answer the question?
Yeah, obviously CD can make some comments.
Well, it's a very exciting area because by mix different elements, right, you create a new kind of material. The material have, so far indicates the material have very unique properties, have good low temperature properties, okay. Lower temperature is better, okay, because of the deformation behavior. Also, this material can form, if you improve property by adding second phase, you form very complex second phase. This complex second phase property very different from simple superalloy form. They are very, second phase can be element 2, can be very strong and ductile, okay, which is different from like a nickel-3 aluminum type of simple element 2. That's why we can get very high strength and high ductility. I think based on this limited data, we think the future is very interesting.
I think...
Yeah, limited comment.
Yeah. I think when we first thought that high entropy alloys were single phase, there was a rule, there was a way for theory to go in there and seek materials, to seek new high entropy alloys. But we don't anymore. We realize that some are single phase, but a lot are multi-phase, or second phase and so forth. So I think the approach of the materials genome of going in and finding some new fancy alloy is going to be extraordinarily difficult for mechanical properties, because it doesn't depend on simply the bonding, it doesn't depend on the phases, it depends on how they're put together. But what you said, I think, is a better approach, is we look at something that works, like the first high entropy alloys, And then we try to tailor that in the, perhaps a bit more of an educated version of the old-fashioned way of adding an appropriate second phase. But I think it's going to be extremely difficult to go in there armed with any computational approach and try to predict the properties of, the mechanical properties of new alloys, because we just can't get a handle on microstructure. And that's, I say the thing, if you looked at iron carbon, you'd probably say, what the hell, it was no big deal. And yet the complexities of steel and how we can make different properties is very difficult to predict. It's extremely difficult to predict.
So, yeah, maybe it's not that as useful, okay, for structural material. But I tend to agree with Professor Xiaodong, right? Okay, and for especially for perovskite solar cell, then you are talking about you are mixing with a different, it's an ABX3 type of crystal structures, right? So you have a metal, then you have you have a halide, and also you have organic stuff in there, right? So we are now undergoing some of the high throughput, like a combinatorial type of spring, all the different composition. Okay, then you can use photoluminescence method to really study the quality formula of splitting of your composition, right? From that, you can quickly get some understanding about the potentially is the optoelectronic property out of this. Maybe not mechanical property, but then it's a optoelectronic property out of this. Then you can focus on that and try to start to optimize that, right?
Allow me to make a comment to make things clear. So, Material Genome project isn't just go out and just do a blind searching. It is 3 factors in there. So basically, when I started this, it seems to be just experimental high throughput experiment. But now the theory is that I can do high throughput too. But if you put the things we're doing science, we don't need just I only do a blind searching, or the other say I do a totally rational calculation first. So we basically, Material Genome project put all 3 together. Is as long as you can increase the efficiency, use whatever method, use your scientific inductions, basically you're doing rational, doing experiment, whatever you're doing most efficient. We're trying to put all things together. By the end, material science is a multi-factorial, that multi-dimensional problem that human mind may not be able to find a clue of correlation. We're trying to, as long as we have more data, we're trying to have machines to learn this correlation. So that helps us to do science. That's all about material genome. It's not just a one single-sided viewpoint. And by the side, and then there's many techniques, multidisciplinary techniques. So people come together, all contribute to the same problem that may have a help to solve a complex scientific problem. Okay?
I think that's a fair statement. My only question was how you actually do it for structural materials. Because I don't think you can at this point. You know, just one thing, in the States now, the mantra for the materials genome.
You choose a seat next.
Yes.
Or not.
One table.
Well, after a glass of wine, okay, I think that you
So, any comments from the lab side?
As I mentioned in my presentation, the property of materials is not only depending upon composition, even within a single composition, even a single element, you can change the lattice structure. You may have different phase, different lattice structure. And also you may have, even you have a single phase, you may have a different morphology. It means different size, different shape. Even with the same morphology, you may have different distribution, spatial distribution. All of these parameters will change the property and the performance. So that means with one single element, you can have a very large property window, property envelope so that can cover a wide range of property and performance. So how can we predict this?
Okay, if you want to.
One answer, yeah, Professor Lu, a very good comment. For example, I said in there, not only composition determine the property, that's exactly. So in our facility, for example, we can do even just chemical growth. We just grow one compound, one single element, just graphite, just for example, right? I mean, we can change the condition of growth. But changing many parameters, temperature, plasma strength, and anything. So we can basically, in one fiber, carbon fiber process, basically there's about 3,000 parameters when we're making this. It's in one single element. So we can change that during process and doing many samples. Just only we examine the sample much more faster. Now doing the conventional, we make one group, one big large fiber, then we measure once. It takes a day. We measure it in a second. So that way we collect more data.
Okay. I like to make a comment that in the early days of high temperature superconductors, the group who won the Nobel Prize was not the first group to look at the ceramics. There was a French group look at essentially the same material, but they overlooked the superconducting property. So one merit I can think of Material Genome project is that for a well-characterized material, you understand their certain properties, and you can carry out the first principle calculation to look at other properties, and that might be very profitable. That's one approach I would think of.
Yeah, there's high throughput calculation.
Right,
also.
right.
Yeah.
So in my view, the use of doing a lot of these high throughput experiments and computations is just as a way of generating data for which you can then mine for correlations, and only for correlations, and only in the variables that you're controlling. So since it's basically a correlation approach, which is where it's effective. The machines are much better at doing correlations than the human mind is. And as long as we define the question appropriately, I think there's a space for this. It doesn't mean it's going to replace sort of the procedures we use now, where we intelligently design microstructure. Yeah. But it's just a way to automate the ability to do correlations. I think as long as we're limiting it to that, I think we're in a pretty good place.
I think you're right, but the mantra in America now for the Materials Genome is we're going to make things twice as good at half the cost. And that's, I think, the problem, because they're not.
Right. That's the salesmanship.
I'll make comment, okay? For the Professor Lu-Juann's point, I agree. The design material can use single element, no problem. Can control microstructure, even control grading, right? Layer structure is fine. But there's one problem. You cannot achieve the goal to use this material high temperature, because stability. That's what we develop a superalloy. You need to precipitate the pin, the kinetic. Okay, so that's the only difference. Given, okay.
Yeah. May I slightly make a comment on CT's question? Yes, you are perfectly right. I'm not saying we can use in pure element to do anything. I just want to demonstrate we can vary the property, the performance, using the very simple composition. Of course, for engineering materials, we do need something else to stabilize the structure. the second and third elements is very useful. So in my slide, in the last slide, actually the last item is I forgot to mention is we should combine the two approach and make a best use of two approach, not only one.
Anybody who have any comments, Professor Liang or Professor Jian?
Yeah, I think all these two so-called material genome approach can be used to accelerate the development of new alloy. But I think although we develop a lot of things, but AI is not yet so powerful. But I think it's in the right direction to because otherwise we cannot test all the combination, even based on our imagination. So in my talk, I just show one dual phase, but with the same target, actually we can produce from metallic glass to 100% crystal with different infinity combination. But all this depends on the dynamic of the processing. So this tool may accelerate and select some and collect data, and so that may help us to develop faster new alloy. Of course, to me, it's like a computer. It's AI adds new material design, but that cannot replace everything. To me, it's like TEM, like other tools. It's another powerful tool if we use it appropriately, because the computer power is now much more powerful than say 20 years ago, and because also the algorithm is more powerful thanks to the speed of computation, and also I think the computational material progress also a lot. So I think we need to move forward by integrating all these approach. Yeah.
Yeah, I probably would like to address Luca's question. How do we input the microstructure into the material genomes calculation? I think there are some empirical rule, between the microstructure and also to the mechanical properties, say like the one you show, the grain size and the hardness or property. There are some fundamental rules you can input into a computer, right? So, and also I also like to address, even we do the mechanical property testing, we're using very small materials, and they can be very, piece by pieces. So in fact, and when we use the metal for engineering application, actually we're using big pieces. So I don't really know how do we correlate the experimental measured mechanical property to big pieces of the metal we're going to use. Okay.
It's doing that, right? Maybe Professor Liang, do you have any comments? I know you are tired because you have 2 talks today.
No, I learned a lot in here, but the main message I learned, our field has been quite empirical. And I think for us, the future is really try to catch up with the theoretical efforts that you guys have made, partly because our system is more complicated, because they are the cellular components that are very difficult to model.
But that's a cutting edge area now. I think the union of engineering or physical sciences and biology, they're almost orthogonal fields. When I was in England, I was a material scientist or metallurgist, and my engineering friends would always say, we know what a metallurgist is or a material scientist. It's an engineer who can't do math. And my response was, you've never met a biologist.
Any question from the audience? A lot of people are smiling here since they're They have something in mind.
Can I have a question for CT? Yeah, can I have a question for Professor Liu? So, yeah, as I remember, you mentioned that hand chip alloy might be the solution for a lot of questions for structural material that we are currently using. So, why you're saying that, and how is that? I was wondering. So, how hand chip alloy can solve all the problems?
I mentioned already, we solved 3 critical problems already by adding nanoscale particles to the high entropy base material. Okay, I did not discuss one point. First point is a high temperature property. Okay.
Okay.
So these have very beautiful properties. How these
high temperature
high entropy alloys with a nanoparticle, how are stable at high temperature, can achieve the good strength, stability compared with nickel-based superalloy.
Okay.
But I think we can do it. We haven't done much yet. For instance, we generate lots of gamma prime phase at low temperature, but at a high temperature it disappears. Okay. How much left? How can you control? Use your genome, material genome, right, to many compositions and try to see what composition give you best stability of gamma prime at high temperature. Then we have a chance to get a really good property. Okay. So that's the point.
Thank you. Thanks.
And
Now I have last one.
okay, no, because somebody else is raising the hand. Yeah.
In solar cell, actually, we try to convert the photon to electrons.
Yes.
Now, if you make the solar cell to be transparent, all the photon are going through your solar cell. How can you generate electrons?
So if you look at the title of that, of course, semi-transparent solar cell, right? So means it's not complete transparent, right? Because you only need about 30%, okay, of the transparency, just like you have a tint window, right? Okay. So even it's dark, you still can see it perfectly outside the environment, but also you can see it in the neutral tone, like a neutral tone filter, right? So you can replicate all the real colors in that. So we are focusing on, that you would like to have semi-transparent solar cell with about 30% or 40% transparency. Okay. So it's never be 100% transparent. That's glass, right? Okay. That doesn't have anything.
Any question for the students? Okay, Thomas.
Yes, I would like to ask about plasmatronics. So I would like to ask about using plasma to enhance the catalytic behavior of hydrogen production. So normally I see this problem as like a chemical service problem. So does the plasma side of things actually improve the efficiency of converting, hydrogen production?
Well, at this time, there is no very little, relatively little commercial production because there are fundamental issues in the material property and also the processing issues. Particularly, it's difficult to find a cost-effective way of producing the kind of structure and the material you need. So that is the part, a big challenge at this time.
It's from undergrad, junior year. Anybody from PhD or master's degree student? Yeah. PhD student? If you ask a question, I will tell you an advisor. No? Yes, okay.
I'm not a student.
Oh, no.
I do have a question for Professor. This one. I do have a question for Professor SROLOVITZ. So when you showed the modeling, so is that in one metal only? Oh, sorry. I can't speak right. Is that for one, like the same atoms everywhere, the same type of atoms? So like all iron or all?
So most commonly that's what we do. On the other hand, we've done this in ordered alloys. as well as some solid solution alloys. But you know, in my experiences, it's not really about which method you use. And the real challenge, I think, is taking from the kind of information you get on the atomistic scale and then integrating up to a more macroscopic scale. That's kind of omnivorous in the sense that it doesn't really matter what you do on the atomistic scale for that level. What you do on the atomistic scale, then it depends on the details. And if you do a lot of the alloy kind of work, then it becomes much more important to do the do first principles calculations to go with it. So the real, a lot of the work we do is first principles, atomistic, microscale, all the way up to continuum properties, and it's the integration that really is, I think, the most important part. And a couple pieces of that are very sensitive to exactly what the composition is.
I guess I was asking because of all of the high-entropy alloy stuff, and I know they're not, maybe they have local chemical order or something.
Yes.
They're disordered, but not randomly disordered. And
Yes.
I was wondering whether the behavior would be the same if you had all of these different.
Right. So introducing composition in that way makes for some interesting things to look at. So, for example, one can look at, for example, I think CT mentioned issues associated with looking at the effect of composition on stacking fold energy. Then if I know what the variation, the stacking fold energy is, then I can do a continuum model that includes the statistics of that variation in it. So it's that kind of combination, but you have to know which property you want to look at. I can't do an atomistic calculation and then just right away from that make predictions on the macro scale. It's the integration that's the important step.
Okay, I think time's up because we do have a dinner banquet. Yeah. So let's give a big hand to all speakers and all the audience. Thanks for attending.